So the next thing that they evaluated was what is the right fine-tuning strategy to use, right? And so far we have seen the following fine-tuning strategy, that you pre-train it, right? And in this case, they pre-train using the C4 dataset. They have an encoder-decoder model and the denoising objective. And then you're going to fine-tune on individual tasks, right? So you take each of these tasks, you fine-tune for that task and update the parameters. So that's something that we have seen before. And they had kept this again to keep all things equal while comparing. They had ensured that there are 2 raised to 19 steps for which the model is trained and 2 raised to 18 steps for which it is fine-tuned, right? So that all things are comparable when they are evaluating multiple different fine-tuning strategies, right? Now, full fine-tuning, of course, is computationally expensive because you have a 220 million parameter and you're going to update all the parameters of the network. So, is there something else that we can do, right? So, the first thing that they tried was using something known as an adapter, right? So, let's understand that. So, this is one layer of the transformer network, right? And I'll just, for the time being, remove this adapters, right? So, this is what one layer looks like. Now, this one layer may have some number of parameters and I do not want to adjust all of them, right, because adjusting all the parameters during backpropagation, if I want to change all the parameters, those many gradients need to be computed, those many updates need to be made, right. So, I do not want to do that, I do not want to update all the parameters. So, can I make a minimal change to the architecture, introduce some new parameters which then become task parameters, right. So, these are the parameters, this is my general model which understands language well. Now, you want it to do sentiment analysis and you are going to show me some data for sentiment analysis. So, I will add some new parameters to this model, okay, and this addition should cause minimal change and we will see what we mean by that minimal change. And now, you just train these parameters while keeping everything else constant, right. So, this model knows how to, what language, what means, or sort of has an understanding of language. Now, for sentiment analysis, just add a new set of parameters which allow it to learn that, right. So, that is the idea behind adapters and that is what they did, right. But now, what do we mean by this minimal change? So, let us understand that, right. So, the input to this layer would be something which is of size D model, right. So, this every token sort of if you remember, so we have these input tokens and each of these tokens is represented by some embedding and that embedding size is D model, right. And now, you are going to do a series of operations. So, you pass this and you get a new representation for each of the tokens, right, and that representation also has to be of size D model, right. So, that is what your expectation is. So, when you are doing any changes, first thing is to make sure this expectation does not change, right. So, the multi-head attention takes inputs which are of size D model, then also produces in outputs which are of size D model. Then the feed forward neural network, if you remember, it takes an input, then compresses it and then again gives an output. So, the output of the feed forward network is also of size D model, right. So, this is of size D model. That means the layer norm which comes after the feed forward network also expects an input of size D model. The layer norm also produces an output of D model which goes to the next layer. So, this layer is also expecting an input of size D model. This layer also produces an output of size D model and which goes to the layer norm. So, the layer norm expects an input of size D model and then again produces an output of size D model, right. So, these expectations should be met. That means, at every layer, if you are going to add something new, the existing layer's expectation should not be disturbed, right. Suddenly, it should not be that layer norm is not getting an input of size D model, right. So, that is what I mean by a minimal change while not affecting the rest of the network, right. So, let us see how they do that. So, they add an adapter layer. So, this adapter layer is now visible. Oops. Yeah, so, this adapter layer is now visible and what is the adapter layer? It is actually just a dense ReLU dense layer, right. So, what does that mean? Let us see. So, this adapter layer is getting input from the feed forward network. So, the input is of course of size D model, okay, and then it has a feed forward network. So, it takes this D model sized input, pass it through a feed forward network which gives a D dimensional output, right. Then it adds a non-linearity on top of it. So, this is D dimensional. So, if you add a non-linearity, it is a element wise non-linearity. So, again you will get a D dimensional output here. that d-dimensional output passes through a feed-forward network which up projects it, right. So that means it again give me a D model sized output, right. So the input is D model, the output is also D model, and you can see where I am going with this, right. So let's see, the feed-forward layer was expected to produce an output of size D model. That's what it has done. Now the next guy has to make sure that it can deal with this output, and that's what it is doing, right. So the adapter layer expects a D model sized output, right. Then this addition here was again expecting a output or an input of size D model. So the adapter layer actually produces an output of size D model, so nothing changes as far as its expectation is concerned, and hence the next guy, which was a D layer norm, which was expecting an input of size D model, gets it, right. And the same argument holds for this adapter layer also. The feed forward network here was producing an output of size D model, which this adapter layer takes as input and again produces an output of size D model, so that the expectation of this guy is met, right. So you have just introduced these additional parameters, which are just the weights in the feed forward network, right. The weights which take you from D model to D and then take you from D to D model. This is of course just the ReLU activation function, so there are no weights here, right. So this is all that they did. They added these additional parameters, and now they just when they are fine tuning, they don't change all the weights in the network, but they only change the adapter layers, the parameters in the adapter layers, and the normalization, layer normalization parameters, right. Whatever parameters are there in the layer normalization, those get updated and the adapter layers get updated. So nothing changes in the multi-head attention weights, nothing changes in this feed forward layer, nothing changes here. Only the adapters get updated and the layer norm, which has minimal parameters, gets updated. So overall the adapter only has like 0.5 to 8% of the parameters in that transformer layer, right. So in every transformer layer, the adapter that you have added only corresponds to 0.5 to 8% of the parameters, right. So not a lot of parameters are getting added. So it's now a very few number of parameters which need to get updated during the fine tuning stage, right. So this is another popular strategy where you add adapters and don't update the entire network, but just a subset of parameters that you have introduced, right. And now here of course this D that you had here, you could variate. The larger the size of D, the more the parameters you would have, right, because the feed forward network here would take a D model size input and give you a D dimensional embedding. So that would just happen by multiplying this D model sized vector by a matrix of size D cross D model, right. So if you multiply a matrix of size D cross D model with a vector of size D model cross 1, you will get a vector of size D, right. So this W is the new parameters that you are adding, and now the larger the size of D, the larger is the weight matrix that you have. That means more parameters you will have, right. So that you can control by changing the value of D. So this is indeed what they did. They did experiments with multiple different values of D starting from 32, 128, 512, 2048, and they observed that none of this actually compares, or there is a significant drop in performance as compared to tuning all the parameters. And as you increase the number of layers, in some cases it helps, but for some tasks a lower value of D is okay, but in general this is not very useful, right. At least at that time, just full fine tuning, you were not able to match the performance by only changing a subset of parameters, newly introduced parameters in the network, right. So then they tried another strategy which is called gradual unfreezing. So in gradual unfreezing, you freeze all the parameters across all the layers and then you gradually unfreeze the parameters. That means as you are seeing the training data, for some number of steps, you will only update the parameters of the last layer. You will not update any other parameter. Then after some number of steps, you will start updating the next layer. Then after some number of steps, you will start updating the next layer and so on, right. So unfreezing happens simultaneously for the kth layer in both the encoder and the decoder. So you have started fine tuning. So first you are going to unfreeze the last layer. That means that whatever parameters are there in the last layer, only those will get updated during the backpropagation. All the other parameters would be frozen. And you are going to fine tune for a total of 2 raised to 18 steps, but you have 12 layers. So each layer would only get updated for 2 raised to 18 by 12 steps, right. So For the first 2 raised to 18 by 12 steps, you would only be changing the parameters of layer 12, then you would only be changing the parameters of layer 11 and so on, right. So, this of course at throughout the training you are not updating all the parameters. So, both with the adapters and the gradual unfreezing, you are reducing the computational cost because you do not have to update all the parameters, you do not need to compute all the gradients, right. And with this gradual unfreezing, again there is a drop in the performance, not as drastic as what they had with the adapter layer, and maybe a better schedule if you had used, you could get a better performance even with the gradual unfreezing, right. But all of this conclusion is that all parameters, updating all the parameters during fine tuning seems to be the best strategy as opposed to using adapters or gradually unfreezing, even though the latter has some computational benefit. But if you are looking at performance, then it is just wise to just fine tune all the parameters of the network, right. Okay. Now, one point here, now some of these observations, these are based on the T5 paper, which is 2019-2020 timeline. Many of these observations may have changed over the years, right, because we are talking about a model of a certain size, training data of a certain size, and today adapters are a bit popular, but again, at least in my experience, the performance that you get by just adding adapters often falls short of what you get by full fine tuning. And also the computational savings are not really that much, because when you're using adapters, often you need to train for a bit longer for convergence. So, it all sort of is not like a very clear winner there in terms of the amount of computational time that it saves, right. So, yeah. But anyways, they decided to fine tune all the parameters, right. So, I'll end this video here, where among all the fine tuning strategies, the one which fully fine tunes actually won in the study in that they had done.